Hello, class. In organic chemistry, there are many ways to represent molecules, and we need to be able to do all of them. And so I want to go through an example of one molecule and look at the various ways you can draw that molecule. And what we're going to look at is isopropyl alcohol. That is the rubbing alcohol that you buy from the stores to clean up a wound or to clean an area of skin before you get a shot or anything like that. So the molecular formula of, let's see, is this going to be a good marker? Let's check it out here. C3H8O. So that, I got to focus here. Okay. This is going to be the molecular formula. There's our molecular formula of isopropyl alcohol. Now the only information that tells us is how many carbons, hydrogens, and oxygens. Like, it doesn't tell us the shape or the structure or the three-dimensional features of this molecule. It just says, boom, there are the atoms in that molecule. Now, could you look at that molecular formula and say isopropyl alcohol? No, you couldn't. You could only say that there's 3 carbons, 8 hydrogens, and 1 oxygen. But if you go to what's called a condensed structure, it's going to start showing us the connectivity and what that molecule looks like. So we have a CH3, and we're going to have 2 of them. And so I'm putting it in parentheses and doing a subscript 2 just to tell me that I have 2 of these CH3s. And then we have a CHOH. Now, if I did this correctly, we should have the exact same amount of atoms in the condensed structure versus the molecular formula. So if this carbon here counts twice, there's 2, 3. I have 3 carbons. And how many hydrogens do I have? Well, there's 3 times 2, that's 6, 7, 8. So 8 hydrogens and 1 oxygen. So it all has to match. That's called a condensed structure. And then we have something called a partially condensed. A partially condensed structure is one where we start drawing out the bonds. You see how there's no bonds or sigma bonds? So I'm going to run out of space there, so I'm going to draw it below it here. So partially condensed structures. I'll take like this. The oxygen has a lone pair, 2 lone pairs, and CH3, H3. And then 1 hydrogen. That also is isopropyl alcohol. Now pay attention. See how this is CH3, and then this is on the left side of the molecule. So why don't I write it like this? Because we read from left to right, right? The reason why I don't like drawing it like this is because this sigma bond right here, the way it's drawn is implying that you're forming a bond with that one of those hydrogen atoms. And that's one of the cardinal rules that we cannot break. And that is a hydrogen atom can only form 1 bond. If I took that hydrogen and said, hey, let's form it to another carbon like this, do you see how that hydrogen right there has 2 bonds? That's not possible. And so when I draw it like this, what's happening is this hydrogen here, one of these hydrogens is bonded to this carbon, and then it looks like it's bonded to that carbon as well. And you cannot have 2 bonds per hydrogen atom, only 1. So that's why I draw it like this, because we're going to have a carbon bonded to a carbon and then H3. Now, these, whenever you see a CH3, like that, it has a special name, and we call those methyls. And it looks like I got cut off a little bit from the screen. So these are called methyl groups. So we could just say methyl groups. Now we could even get some more information by drawing the Lewis structure. And the Lewis structure is when we expand out all the atoms and show all the bonds. So what we have is this methyl group right here. I will represent it like this. You see how there's 3 hydrogens? 3 hydrogens, 1 carbon. That carbon is bonded to another carbon, so I'll draw that. And that carbon is bonded to an oxygen atom like so. It has 1 hydrogen and then another methyl group. So there's isopropyl alcohol in its Lewis structure, completely just drawn out. So when you take a look at these structures here, you can see that the Lewis structure gives us the most information. The molecular formula gives us the least amount of information. When you take molecules, however, and draw them out using the Lewis structure, it takes a lot of time. A lot of time, because you're drawing all the bonds, you're drawing all the atoms, you're drawing all the lone pairs. Just a lot of work. And so what has happened, in order to give us all the information in this Lewis structure, but draw it more simply, we've come up with something called a zigzag structure. A zigzag structure. It also goes by the name of a line structure, or your textbook refers to it as a bond line structure. A bond line. That is a horrible way. A bond line structure. And the bond line structure for isopropyl alcohol looks like this. And I'll draw it in a different color and put it right here. So the bond line structure for isopropyl alcohol looks like this. And you can see where the name zigzag, it's just boom, boom. It's zigzagging. So that is another way to represent isopropyl alcohol. And depending on the question or what you're trying to do, each structure has its pros and cons. But more often than not, organic chemists, when they want to discuss and show you a structure, they're going to use this zigzag structure. Because did you notice, if you took like a stopwatch, how long did it take me to draw this guy versus this guy? Do you see how fast I can draw isopropyl alcohol? It's just boom, 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 done. Compared to having to draw all this out and drawing in the lone pairs. So this is where we want to get to. We want to be able to go between all of these structures except for the molecular formula, because that one doesn't tell us the structure. It just tells us how many atoms there are. So what we want to be able to do is, if I gave you this condensed structure, could you draw me the zigzag? Or if I gave you the zigzag, could you go and draw the Lewis structure? So we want to be able to use all of these interchangeably. But when we're trying to be quick the best way is to use our zigzag structures. So how do I know this guy right here is representing this? Well, we will get to that after I discuss with you some major rules that you need to be aware of and need to be reminded of. Some of these you have learned from general chemistry, and we just need to remind ourselves of these ideas here. So let's just enumerate them. Rule 1, carbon atoms have 4 bonds. Carbon atoms need 4 bonds. So what does that mean? A carbon atom with 4 bonds directly attached to it. It has to have 4. Now this rule right here, the first one that I'm talking about, for right now, that's the law that you're living by, 4 bonds. Now that law is going to change as we progress through the course. But for right now, remember, carbon needs to have 4 bonds. The second rule is hydrogens can only have 1 bond. And I already discussed an example of 1 bond for every hydrogen atom. You cannot do double bonds or multiple bonds on a hydrogen atom. The third rule that you need to be aware of is oxygen atoms. Oxygen atoms can have 2 or 3 bonds. There's another very important rule, is your halogens. And halogens are simply more often than not represented by just a capital X. And so X would equal fluorine, chlorine, bromine, and iodine. Those are the halogens. Halogens also are like the hydrogen atoms. Only 1 bond. So if I had a molecule that looked like this, you see how fluorine is bonded to a carbon atom via a sigma bond. Only 1 bond. I want to contrast that. What if you tried to draw a molecule like this? What is wrong with this molecule? It's breaking the 4th rule. You cannot have a halogen with 2 bonds. Only 1. And then the 5th rule, it is a very important rule to remember. And it kind of goes along with rule number 1, is that 4 bonds. Sometimes people like to form what's called a Texas carbon. And a Texas carbon is simply a carbon that has 5 bonds to it. You cannot have 5 bonds on carbon. The max is 4. And so we're going to go through some examples and look at what a Texas carbon would look like. So let's maybe take this molecule right here, and just draw a Texas carbon so we can get a better visualization of what's going on here. All right. Let's draw a Texas carbon. So what if I put another carbon here, and then I go 1, 2, 3, 4. So let's just start from the left. So I'm just looking at the carbons. Here's a carbon. How many bonds are around this carbon? 1, 2, 3, 4. Perfect. This carbon. 1, 2, 3, 4. Done. This carbon. 1, 2, 3, 4. Perfect. Come to this last carbon. 1, 2, 3, 4, 5. That right there is a Texas carbon and does not form. It cannot form because carbons can only have a max of 4 carbons. So if I wanted to fix that, I would just erase these hydrogens right here and just draw in only one of them. So now that is a beautiful carbon and not a Texas carbon. Okay, so those are the rules. So now let's show you how to look at a Lewis structure and convert that into a zigzag. Okay. And the way you do that is, let's get this back to isopropyl alcohol, shall we? What you do is you count how many carbons there are in like in the longest chain. So do you see here, if I just considered this a chain of carbons going from left to right, you see that I can count 1, 2, 3. There's 3 carbons in that longest chain. And so what you do is you have to draw 3 carbons in the zigzag. And every point on the zigzag represents a carbon atom. So if I color code or number these, if that's carbon 1, carbon 2, and carbon 3, every point on this zigzag represents a carbon. And so that's carbon 1, carbon 2, and carbon 3. And on carbons 1, 2, and 3, do you see in the zigzag, I don't draw any of the hydrogens. On zigzag structures, you don't draw hydrogens. They are just implied. Now let me restate that. Hydrogens attached to carbon atoms are not drawn. They are implied. But if the hydrogen atom is attached to a heteroatom, like this, then you have to draw on the hydrogens. So I use the word heteroatoms. Heteroatoms are all atoms except carbon and hydrogen. So halogens, so your chlorines and your bromines. What if you want to put phosphorus or sulfur or a metal like magnesium? Whenever you have heteroatoms, which are non-carbon, non-hydrogen elements, you have to draw them out in the zigzag structure. Now I could draw it like this with the oxygen-hydrogen bond. I could expand it out like that if I'd like, or to save time and ink, can just represent it like that. Because I'm looking at this oxygen right there, and it's right there as well. Now on the zigzag structures, you can put in the lone pairs if you'd like. I think it's a good idea to put them on the zigzag structures because you're going to need these lone pairs in the future. And so it's a good idea to know how many there are. And so in order to know how many there are, you need to go back to general chemistry and review formal charges and how many lone pairs are around atoms. And we will touch on that throughout the course. But right now, the point of this lesson is to show you that hydrogens attached to heteroatoms need to be drawn, whereas hydrogen atoms that are attached to carbon are not. So that's how you draw the zigzag structure. And we've numbered the carbons, so you can see that. You don't draw on the hydrogens. But as you're learning this, you need to be able to look at a zigzag structure and know exactly where the hydrogens are and how many there are. And so if you have to draw them in until your brain can start seeing what's happening here. So this is carbon 1. How many hydrogens are attached to carbon 1? Well, if we go to the Lewis structure, it's easy to see. 1, 2, 3. But in the skeletal structure, you don't draw them in. But remember the rule that carbon has to have 4 bonds. So if I represent this carbon right here like this, and that carbon is then bonded to this carbon, and then that carbon is bonded to that carbon, and I've ran out of my board space here. Let's do it down here, shall we? So carbon 1 could be represented like this, carbon 2, and then bonded to carbon 3. And then to carbon 2, which is the one in the middle, what do we have? An OH, like so. So this zigzag structure is saying, hey, carbon 1, when I draw it just like this and not drawing any hydrogens, how many bonds does this carbon have? It only has 1 drawn. But we know carbon has to have 4 bonds. So this is carbon 1. And if I draw in the hydrogens, those 3 hydrogens are still there. They're just implied. And then here, carbon 2. Look at carbon 2. How many bonds are there? 1, 2, 3. But I've said there has to be 4. So that means there is a hydrogen that's implied. We go to carbon 3. We see that there's only 1 bond, but it has to have 4, so you fill them up with hydrogens. So you could, in theory, take a zigzag structure, and this is for your own learning ability, or this is for you to make sure you understand what's going on, is you could, in theory, draw in your hydrogens. And why do I want you to draw in your hydrogens? Because there will be a situation where I will give you a zigzag structure, just like this isopropyl alcohol. And I will ask you, how many hydrogens are in this molecule? And you'll be like, okay, well, I got to count them. And you'll be like, okay, there's 1. So let's do it in this blue structure. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hydrogens. But you got to be able to do it in the zigzag. So you'll get really good at this. You'll be like, there's 1, 2, 3, 4, 5, 6, 7, 8. But until you get really good at it, it's okay to take a zigzag structure and draw in your hydrogens. Okay? So now let's look at another example here on what I expect you guys to know. So what we have here is a condensed structure of a molecule, and I want you to be able to look at that condensed structure and convert that into a zigzag structure. The way I do this is I start numbering the carbons that are not in parentheses. So 1, 2, well, let's see here. Not only the carbons, but I'm also going to number this oxygen because it's not in a parenthesis. So 4, 5, 6, and 7. Now remember that when we convert this to a zigzag structure, each point on that zigzag represents a carbon. And so when I go like this, just draw a line. Like, well, let me start off. Let's see here. So when I look at this structure here, I see that whenever you have parentheses, that parentheses is going, that group inside the parentheses is going to be attached to the carbon that is right before it. So here's the parentheses, so right before it, it goes on this carbon. Once again, now we see carbon 5 has a hydrogen and a parentheses. So this methyl group, because it's a CH3, is going to be attached to carbon 5. Whenever you have parentheses on the outside of the carbon, of the molecule, like these two right here, those methyls are going to be attached to carbon 1. So what I can see here is I have a carbon 1, and I have a CH3. I have a methyl group directly attached to carbon 1 and another methyl group. And then carbon 1 is bonded to carbon 2. And carbon 2, if we number these, carbon 1, carbon 2, what is directly attached to carbon 2? This methyl group. So I'm going to draw it up here. And so that, the parentheses is attached to carbon 2, but this carbon right here, carbon 2, is also bonded to this oxygen. Now let's keep going here, and we'll come back to this. So that's oxygen 3, and then that is bonded to carbon 4, and carbon 4 has 2 hydrogens on it. Those 2 hydrogens right there. And carbon 4 is bonded to carbon 5, which has a hydrogen on it, which also has a methyl group attached. And then that carbon right here, so that's carbon 4, that's carbon 5, and that is bonded to carbon 6. And look at this. This is kind of tricky. The way this is drawn, it kind of implies that it looks like this, right? That does not work. Why does that not work? Because hydrogen has 2 bonds. We've broken that rule. Can't do it. We've also, in those list of rules, I said oxygen forms 2 to 3 bonds. That only has 1. So that cannot work. So what happens is we look at a different Lewis structure. What if we draw it like this? And that would be oxygen 7. That does work. Why? Because now oxygen has 2 bonds, like it wants to have. Hydrogen only has 1 bond. And carbon 6 has how many bonds? 1, 2, 3, 4. Has 4 bonds. It's happy. So now as we look at this Lewis structure here, are there any carbons without 4 bonds? 4, 4, 4. Oxygen atom has 2 bonds. It's happy. Carbon. How many bonds does this carbon have? 1, 2, 3. So that doesn't work. How many bonds does this carbon have? 1, 2, 3. But when we look at carbon 1 and carbon 2 here in the formula, are there any hydrogens attached to it? There's not. So what we have to do is add a pi bond or a double bond. And now that double bond right there, now look at carbon 1. It has 1, 2, 3, 4. Carbon 2, 1, 2, 3, 4. So it is satisfied. And now what we're going to do is, now that we can kind of visualize this, now we can convert this into a Lewis structure or a zigzag structure. So the way I like to do this is I just start drawing my zigzag here. So if I start at this carbon right here and draw a line, this carbon that I'm pointing to is that carbon. And that carbon is directly bonded to that carbon, which is that carbon. And then we can go zigzag now to carbon 2. So we could call that carbon 0, 0, 1, and 2. Now carbon 2 is directly bonded to oxygen, so we just have to draw the heteroatom, and then we're bound to carbon 4, carbon 5, carbon 6. So if we number these, 4, 5, and 6. Now, if I take a look at carbon 1 and carbon 2, what is missing in my zigzag? The double bond right there. And then attached to carbon 2 is what? A methyl group. So we just have to put a line right there. So this line right there is this methyl group right there. Attached to carbon 1 is this methyl group that we haven't worried about yet. So I'll just draw in a line. So that point right there represents that methyl group. So I'm just going from carbon 1 to making sure everything matches. Methyl, 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 double bond, carbon 2 directly attached to an oxygen, oxygen, and then carbon 2 has this methyl, which is right there. And I just keep going down the chain. Okay, this is carbon 4. What's attached to carbon 4? 2 hydrogens. Do I draw them in? Nope. Carbon 5. Carbon 5 has what? A methyl group. So I have to draw a methyl group. Do I draw in this hydrogen on carbon 5? No, I don't. It's just implied. And then carbon 6 is this guy. And with carbon 6, we have to draw in all our heteroatoms. So I'm going to do our double bond O. And so that's carbon 6 and oxygen 7. Now this hydrogen right there is attached to carbon 6. Do I draw it in like this? Do I have to? No, you don't have to, because hydrogens that are directly attached to carbons are implied, and we don't need to draw them. But do you need to know that a hydrogen is there? Yes, you do. You just don't need to draw them. So that right here is the zigzag structure of the condensed structure. So you're going to get a lot of practice going from these condensed structures to the zigzags. But you also have to get good at going from the zigzag to the condensed. You have to do it in both directions. And you will find that in organic chemistry. When you're learning something in the forward direction, also learn it in the reverse. Make sure you can do things in both directions. Okay? Let's see here, time-wise here. I think we have time to do another example. Okay, in this example, you just number the carbons like I did last time, except the ones in the parentheses. So 1, 2, 3, 4. Let's see here. What am I? Let's double check something here. Okay. So what that's telling me to do is draw a zigzag with 4 carbons. Like this. 2, 3, 4. To see if we number that now, I have 1, 2, 3, and 4. And now I just need to make sure the connectivity is right and that I've accounted for these groups that are in parentheses. when you have a CH2 and a CH3, that is called an ethyl group. And ethyl stands for 2 carbons. And here we have a second ethyl. So what kind of terminology have we learned so far? This group right here is called a methyl. When you have 2 carbons, CH2 and a CH3, that's called an ethyl. And so I'm seeing carbon 1 is a methyl here. Carbon 2 is bonded to carbon 3. But what's also attached to carbon 2? Well, this group, the ethyl group in parentheses, is going to be attached to the previous carbon, which is carbon 2. So it's just 2 carbons. So I have to just draw in 2 carbons off of carbon 2. So 1 carbon, 2 carbon. So if I start that guy, that would be that guy right there. And if I put a little triangle there, it would be that carbon there. Then I go to carbon 3, which is attached to carbon 4. And now look at this. Carbon 4 is attached to 2 ethyl groups. So ethyls are 2 carbons, so 1, 2. But there's this subscript right there that says I have 2 of them. So I just draw 2 more. 1, 2. So if we color code this here, we could, let's just say that's a dot. So that would be, we could represent that one there, and then an X right there. But then there's 2 of these. So there's the other dot, there's the other X. So that right there is the zigzag structure for this condensed formula. Now I want to make sure that when you look at a zigzag, you can tell me and yourself how many hydrogens there are. Right? So let's look at a few carbons here on this molecule here. So if I looked at this carbon, how many hydrogens are on this carbon? Well, in my mind, or I could say, hey, that's a carbon. And that carbon is bonded to this carbon. So there has to be 4 total bonds. So that carbon has to have 3 hydrogens. This carbon right here is bonded to 1 carbon, 2 carbon, 3 carbon. It has 3 bonds. So it has to have 1 hydrogen. This carbon right here is bonded to 1 carbon, 2 carbons. So there has to be a total of 4 bonds. So there are 2 hydrogens. So now you can see this carbon right there in the center has 1, 2, 3, 4. How many hydrogens does this carbon have, do you think? Pause the video and answer that question. You will see that if you do your counting correct, that there are 2 hydrogens. Okay? Now, what we have here is when you have a molecule that is just carbon and just hydrogens, do you see that there's no heteroatoms, no oxygen, sulfur, or anything like that? When you have just carbon and hydrogen, we call that a alkane. And more importantly to understand is an alkane is a molecule with only carbon and hydrogens and only have single bonds. You see everywhere in this molecule, it is just single bonds. There's no double bonds, no triple bonds. So that would be single bonds. Okay. Let's take a look at rings. We can have molecules in the form of rings. Let's take a look at a ring called cyclohexane. cyclohexane. And the prefix hex tells us that there's going to be 6 carbons. So if I have a hexane ring, it would look something like this. So if I did that right, there's 1, 2, 3, 4, 5, 6 carbons in a ring. But each carbon has to have 4 bonds. So if I look at this starred carbon right there, what's so important about this guy? Well, it already has 2 bonds there. So it is implied that there's 2 hydrogens attached. And so every carbon is going to have hydrogens coming off. Do you see how labor intensive this is to draw in all the hydrogens and to draw in all the carbons? So it's just easier to draw a cyclohexane ring like this. Boom, done. We don't have to worry about it anymore. But when you look at cyclohexane, do you see that these carbons right here are all going to have 2 hydrogens attached? Because you have to have 4 bonds per carbon. Now we could have another molecule called benzene. And we could take benzene, and we could draw like kind of doing the same thing as with cyclohexane. We could, benzene is also a 6-membered ring. Like that. But what's different in benzene is that it has alternating double single bonds. So this carbon right here at top, how many bonds does it have that's shown? 1, 2, 3. So that means there has to be 1 hydrogen on every carbon. Now that's very labor intensive. That's benzene. But a better way to draw benzene and an easier way to draw benzene is draw a 6-membered ring and then draw on your double bonds like that. Oftentimes that right there is a little too labor intensive for some people. And instead of drawing benzene like that, you can also draw it like this. Kind of looks like a donut. So that little circle there in the middle there is telling me and telling you that you have a double, single, double, single, double. Could you have drawn benzene like this? Do you see the difference between the two? Both are correct because all you're looking for is double, single, double, single, double, single. If you have a 6-membered ring with that 3 double bonds in there, then you will have drawn benzene correctly. Or if you just draw it like this, that is also benzene. Okay. So we can look at all different sizes of rings. You can have 3 carbons in a ring, so it looks like a triangle. You could have 4 carbons in a ring. You can have 5. And then drawing the 7-membered rings and the 8-membered rings get a little bit more difficult, but you can draw them. So if we take one of these, let's just do this for fun. Let's take a look at this molecule right here, the 5-membered ring one. And that is called a cyclopentane. Pent meaning 5, like the pentagon, 5 sides. How many hydrogens are in cyclopentane? We'll just look at each carbon. How many bonds are there? 4 are drawn, so that means it's implied that there are 2 hydrogens on each carbon. And so how many hydrogens are on this cyclopentane ring? There's going to be what? 1, 2, 3, 4, 5 times 2, so that's 10 hydrogens. Okay? You have to be able to look at the skeletal structures and count the hydrogens. Essential skill. So once you guys get really, really good at looking at skeletal structures and being able to count how many hydrogens and how many carbons there are, we are going to use that skill set to be able to look at a molecule and name it. We need to be able to look at a molecule and say, hey, that thing that I just drew, or that thing that I just made, or that thing I'm looking at, what do I call it? And so we have a rather long list of different types of molecules that you just have to memorize what they are. And get flashcards, write them out. As you're walking between classes, look at your flashcards. Organic chemistry is learning another language, and it's going to just take a lot of time and effort to get this down. So one thing that you need to be able to look at a molecule and identify it as such is something that looks like this. That is called that's not an acid. That is called a alkyl halide. And an alkyl halide is when you have carbons, a carbon chain. In this case, it has 1, 2, 3 carbons, and you have a halogen directly attached to it. So this halogen right here is chlorine in this case, but it can be any of the halogens. So if I represent it with an X, and that X could be fluorine, chlorine, bromine, and iodine. Now, there are millions and millions of molecules, and an alkyl halide doesn't just look like 1, 2, 3. An alkyl halide could be something that looks like this. Do you see how I put the X on the middle carbon instead of the N carbon? I could even have something that looks like this. Look at that carbon chain. How many carbons is that? 1, 2, 3, 4, 5, 6. A 6 carbon chain. That is also an alkyl halide. I could even tack on some other groups. I could even tack on, let's say, a ring. So this molecule right there is a alkyl halide. Just for good effects here, what if I put that halide right there? That is an alkyl halide. So how can you represent basically an infinite amount of alkyl halides? How can you memorize it? Well, it's the generic form of a alkyl halide looks like this, RX. So that R is telling us anything that is alkyl. So this word right there. And alkyl is simply just carbon chains. So this alkyl halide here can be represented like this. And so the R group in this particular alkyl halide is going to be, oh wow, that was squeaky. Let's get a different marker. So what I just put in that rectangle in pink is the R group. And this in green right there, that's the R group. So this massive beast right here, what we would do is be like all of that is the R group. So this alkyl halide right here can be represented like that. So that right there represents a alkyl halide. And when we look at molecules and say, boom, that's an alkyl halide, what we're doing is we're classifying its functional group. I'm running out of space here. Functional groups. So we are going to go through a list of the different types of functional groups that you need to be aware of and be able to identify when you see it. So I'm going to just show you a couple more, and then we will conclude this lesson here. But there are tables in your textbook that talk about and show you all the different functional groups that you need to be aware of. Okay? So let's do a couple more to wrap this up. So what we have is an alkane. And we've already seen that already. That is just simply a molecule with carbon, hydrogen bonds only. Okay? Just anything with just carbon and hydrogens is a alkane. We have something also called a alkene. Do you see how the suffix is just a little bit different? We replace an A with an E. An alkene has a generic representation like this. And this is where the R's in this generic formula can be hydrogen or alkyl. Remember, alkyl is just adding carbons and hydrogens. Or alkyl is adding a carbon chain. So if we look at this generic alkene, we could take it and replace, let's say this R, let's replace it with a hydrogen. This R, let's replace it with a methyl. This R, let's replace it with an ethyl. So CH2, let's see here, how do I want to do it? Let's do it on this side. Let's replace that with a ethyl, CH2, CH3, and a hydrogen. And let's just draw in 3 carbons, okay? That is a alkene. If you have a molecule with only carbon and hydrogens, but you have one double bond anywhere in that molecule, you have a alkene. And the last one that I want to share with you for this video is a alkyne. And an alkyne is a carbon-hydrogen molecule, a molecule with only carbons and hydrogens with a triple bond. So those R groups right there, those R's, they can be hydrogens or alkyl. All right, so let me show you a subclass of alkynes that you need to understand. And then we will be done. We have what's called a terminal alkyne versus a internal. So a terminal alkyne would look something like this. We will go CH3, carbon, double bond, or triple bond, CH3. Do you see how that sorry, I actually drew, no. So this is a terminal. And we call it a terminal because this R right here is a hydrogen. When you have a hydrogen for one of these R's, you have a terminal alkyne. An internal alkyne looks like this. 3 carbon, like that. So when both R groups, and this is the R group, and that's the R group, when both of the R groups are alkyl for carbon, then we call that an internal alkyne. Okay, that's where we will stop for today.